Okay, you got your piece of paper, got your coin. You may not need the coin, but you might. Got your pencil, got your calculator. Once again, if you need to, just Google the, get a Desmos calculator. That's fine. Just need something to do some calculations with. Okay, first step. Pick a number from 1 to 100. When you have step 1 done, type a 1 in chat, please. Write that number down. You can just label the rows. You can label, as you go down on the piece of paper, put a 1 next to this row, okay? All right, step 2. Add 57 to your number and write that number on row 2. Type a 2 when you're done. You're definitely going to want to have a calculator because we're doing some kind of big multiplication and stuff too. Step 3, multiply the number from row 2 by the number 23 and write that down in row 3. Type a 3 when you're done. Okay? Step 4, add the digits of your number from row 3 to create a new number. For example, if your number in row 3 was 2,537, you would add 2 plus 5 plus 3 plus 7 to get 17. Okay, type 4 when you got your new number in row 4. Okay, multiply that number by 7. Write that number in row 5. Type a 5 when you're done. Okay, now step 6, keep only the last digit. For example, if your row 5 number was 158, you would only write down the 8. You only keep the last digit. Write down a 6 when you're done with that, or type 6 when you're done with that step. Okay, now probably you do nothing here. Okay, if your digit is not 0, if your digit is non-zero, do nothing. So most of you are, most likely you're not doing a thing. Okay, if you happen to have 0 for your digit, then flip your coin. Heads means you're going to randomly choose a number from 1 to 5 and write that down. Tails means you're going to randomly choose a number 6 through 9 and write that down. Okay, when you're done with those 2 steps, type an 8, please. Okay. Step 9, multiply your previous number by 9 and write that down. Type a 9 when you're done. Okay. Add the digits. Step 10, add the digits and create a new number. Type 10 when you're done. Whatever number you got in row 9, add those digits to create your row 10 number. Okay, good stuff. Okay, subtract 5 and write that number down in row 11. Type in 11 when you're done. Good stuff. Okay, now we're doing something strange. Now you're going to convert your number on row 11 to a letter. Okay, so for example, if your number's a 1, write down an A. If your number's 2, a B, 3, a C, 4, a D, 5, an E, etc. So you should be writing down a letter in row 12. Type a 12 when you're done. Okay? All right, next step. Now you're going to choose a European country that begins with your letter. Okay, this one's going to be a little bit odd. I think I have to make this, in order for you to be able, I even have a list here, but I think you need to, here, let me do this. Give me just a second. This will help you out a little bit because there's lots of European countries. Okay, see if that works. There you go. So choose a European country that begins with your letter. And if, like, for example, you had, what's a letter that doesn't exist? Like if you had O, for example, there's no European country, then you'd move up to P. Just move up until you find one that works, okay? But whatever your letter was from step 12, choose a European country that begins with that letter and write it down. When you're done with row 13, type of 13. Okay, another odd step here. This is kind of a strange one. Last step, step 14. Now write down the second letter of your country and choose the largest land animal that begins with that letter. For example, if your country is France, the second letter is R, and you'd probably choose like rhinoceros, the biggest land animal you can that starts with the second letter of your country. And write down that animal, please. Oh, I'm getting some strange mental energy coming from the computer here. There's no elephants in Denmark. What are you guys thinking about? That's crazy. They're not indigenous to Denmark. That's crazy. Okay. All right. Just a little fun. Just a little Friday fun. All right. Back to business here. Everybody got elephants in Denmark, didn't they? Yeah, that's what I thought. Okay. If you go back and look at the steps, it's not that tricky. You probably already figured it out. Okay, so where'd we leave off? Last time, a couple days ago, we were talking about using the quadratic formula. So let's get back to business with that. Oh, hey, before I forget also, before we jump into this, because I'll forget if I don't say it now. So I have written the test that's coming up here shortly, and I've got the practice test made. I think it has like lots of parts. I think it had like 9 parts. They're short. Remember why I do this, so you can, so I can give you the exact test environment. It's drawing from the same pool of questions that your test will. So and you can do these as many times as you want. You can pull up questions multiple times if you want to, and if you find a part of it where you need some extra help, maybe you hit that part of the practice test harder than the other parts. I'm going to make it available, but I wanted to let you know I'm making it available. We're not even done with the unit yet, but if people want to start kind of preparing a little bit, so it's not such a big cram session at the end, I'll make it available just for your benefit. So it just makes things a little bit easier for you, so you don't have to, you can kind of spread out the studying if you want to a little bit. You don't have to, but I'll make it available, okay? All right, so here's where we left off. Applying the quadratic formula, right? We derived the quadratic formula by completing the square with our general expression of a quadratic equation in standard form. We solved a quadratic equation in standard form for x by completing the square, and we came up with the quadratic formula result, right? So how do we use this thing? Well, first of all, we always have to start in standard form, right? So if a quadratic equation is not in standard form, we have to put it in standard form. We always want a to be positive, so we will we'll distribute a -1 through both sides if necessary to make a positive, And then we just evaluate the quadratic formula. And so we were looking at an example here. Okay, so we pushed everything to one side and we made things more convenient by clearing the fractions. We distributed a 4 through. So all we have yet to do here now is just evaluate the quadratic formula to get our solutions, right? So what's that give us? So if we plug in, if we plug in the values of A, B, C, and D. Now, what are the A, B, C, and D? What are the values of A, B, and C here? A is, everybody agree it's 1. B is -8. C is 22, right? So we're going to get x equals -b. Well, b is -8, so that's going to be a +8 plus or minus the square root of b squared. So b is -8, right? But when I square a -8, what should I do instead? If I'm taking a negative number to an even power, what's an easier way to do that? -8 squared is the same as what squared? +8. Yeah. So a little trick, whenever you're doing computations in math, you know, where you're just trying to plug numbers in and come up with a result, a good idea is always, anytime you take a negative number to an even power, just evaluate the power of the positive number, and you avoid some arithmetic mistakes then. A really common thing to do is, like, if I were to write in -8 squared, if I forget to put that in parentheses, when I plug this into a calculator to do my computation, I'm going to get the wrong answer, right? So let's just avoid that, avoid having to do all those steps, and instead, let's just never write it as negative in the first place. Just write it as 8 squared, right? So 8 squared minus 4 times a, which is 1. I don't even have to write the 1, but I will this time, times c, which is 22, right? And we end up all of that being divided by 2 times a, which is 2 times 1. So it's all over 2. Now I just have to simplify that. And it, you know, it works out to be the same process every time. So you get real good at this real fast. Well, for one thing, we could go ahead and split this up into 2 parts if we want to. So I get 8 over 2 plus or minus the square root of 8 squared is 64 minus 88 is going to be -24 over 2. So it's going to give me 4 plus or minus. Type in chat for me, please. What is, simplify the square root of -24? And you can just use, like, for the square root part, you can just make it a 1/2 power, right? Anything, the square root of something is the same as taking it to the 1/2 power. So I'll give you an example. Like if I wanted to do, I could do something like that, like 8 to the 1/2. So the square root of 8 is 2 times 2 to the 1/2. Or if you want to, there's another way you could type these in. You can also do it that way. We use an abbreviation, SQUIRT, SQRT. Stands for square root. Squirt 8 equals 2 squirt 2, right? You can write it that way too. So what's your answer? Type in, what is the square root of -24? Okay, good. I'm getting 2 times the square root of 6 is the square root of 24 part, and then the negative becomes an I, and we'd probably put that I between the 2 and the square root maybe, right? So we get something like that. And look, I could cancel those 2's, couldn't I? Right? And so I end up then with x equals 4 plus or minus. And just so this looks like a complex number in standard form, I'm going to go ahead and put the radical first and be very careful to just put the I outside. So look at that. I get 2 results, 4 plus the square root of 6 times I and 4 minus the square root of 6 times I. So the real part is 4. The imaginary part is either positive or negative 6, right? So we get complex conjugate results. Those are my 2 answers. Okay, everybody good? Give me a thumbs up if we're good with that. Okay? Let's try just a couple of those. Okay, let's maybe work through this one. And let's just talk about all the steps to solve this. What can we do first here? Just plug it in quadratic formula? Good. We could divide by 4, couldn't we? Right? And that's okay to do. Right? If we're just trying to find the solutions to this equation, and sometimes I think people, they have a conceptual block with stuff like this for a good reason. If I have some function f of x equals 4x squared plus 30x plus 12. Well, if I divide by 4, I get a different function. Maybe call it g of x equals x squared plus 8x plus 3. Those are different functions. Their graphs would be different, wouldn't they? Right? But if I'm solving the equation, let's say I'm trying to find the zeros of f of x. Well, that just leads to that equation, doesn't it? I'm going to set the function equal to 0 and solve. Okay. If I'm just solving this equation, I could just divide both sides by 4. Right? And that's going to give me x squared plus 8x plus 3 equals 0. And now I can just apply the quadratic formula, right? So I get x equals negative b, so negative 8 plus or minus the square root b squared, so 8 squared minus 4 times 1 times 3, all divided by 2. So that's 8 over 2 plus or minus. I'll tell you, we'll write this one a little differently. And this is okay to do, just to give you a little different look here. Let's leave the top over a common denominator. So I get 8 plus or minus the square root of 64 minus 12 is 52. Well, I know if I take 52, 4 goes into that, right? 4 goes into that, what, 13 times? So I'm going to get a couple 2's, right? So I'm going to end up with 8 plus or minus 2 times the square root of 13 over 2. And now I could just simplify both parts of that fraction, right? I could make that into an 8 over 2, which is 4, plus or minus 2 over 2 cancels, and I get square root of 13, right? Okay, so what's the best way to do it? I think the way we did the last one is slightly preferable, because sometimes you're going to end up, in order for something to be completely simplified, let me think if I can come up with an example here. Like, what if we had something like this? What if we had, let's just say we had something like 12, pick a different color. What if we had something like 12 plus or minus 6 times the square root of 2 over 4? right? This is an example where, okay, you might say that I could divide top and bottom by 2 and simplify that, but you can do more. I would have to split the terms here to write that as a 12 over 4 plus or minus 6 radical 2 over 4. Because look what happens. This first fraction reduces further than the second one does. So I need to write them separately, don't I? In order for it to be completely simplified. I want to split those two terms. Everybody agree? You see my point? Not a big point, but that's why I think it's maybe just a little bit easier to break those up into separate fractions. Okay. Now, when I get situations, the one case where and we'll see, you guys will just kind of work through this stuff. But if I know that I'm going to get an integer coming out of this square root, if I've got a perfect square under the radical, well, then I don't need to split up the fractions because I'm going to get integers on the top that I can sum or subtract to get a single number. And so there's no reason in that case to break it up into two separate fractions. Do you see that little subtle point there? If we're not going to end up with any square roots, if the square root part is going to go away, so I'm going to get rational results for both the first and the second term on the top, then there's no reason to break it up because I can just combine the numbers on the top into a single number. I don't want to make too much out of that, but it's just a little subtle thing in math. Okay, so we got our answers. 4 plus or minus the square root of 13. Okay, so now let's connect that to our original thought up here. Okay, I really want to make this point. This is an important thing in math, but it also is very subtle. So sometimes people have a problem with dividing both sides by 4 because when I do that, I change the two functions, right? If f of x is 4x squared plus 32x plus 12, and if I divide by 4, I get g of x equals x squared plus 8x plus 3, and those are different functions, and their graphs are different, and I'll prove it to you. Let's graph those two. I want to show you. I make a point here. Okay, let's graph the function f of x equals 4x squared plus 32x plus 12. And how about if we shrink that down just a little bit? And then let's add the function g of x equals x squared plus 8x plus 3. Okay, and I'm gonna practice making this graph look better too. This is another skill you guys should start to be developing a little bit. If I want to represent these graphs better, I could go into my graph settings, and I could just go from like -10 to 1 instead of having such a wide range of values showing up on my window of x. I could go down here to the x-axis, and I could choose the x values that are pinched between. I'll replace that left number with -10. I'll replace the right number with 1, and look how it spreads it out. Now, what about on the y-axis? Well, let's say I'm just going to go from, what are we currently at here? We're going from, about 15 down to -20. Why don't I do something like, just to make it look better, I'll go, I don't know if this is going to work or not. The top, well, we can leave at something like 15. Whoops, 15. The bottom, I just always click on the number and then hit Control A to highlight the whole number so I can type over the top. What if I do like -30? Is that big enough? Nope, not quite. -80. There we go. Okay, now I got a better graph. They're different graphs. Look at that. The blue and the red are different graphs. So how in the world can I do this? How can I find the zeros of this function by dividing by 4, because look, I end up getting the zeros of the blue function. But look at this. What do you notice about the zeros of the red and the blue functions? They're the same, aren't they? Everybody agree? Okay, the math gods are wise. They're so wise. The math gods know here that it's okay to do this, because when I do the algebra step of dividing both sides by 4, yes, I'm trading the red function for the blue function, but it doesn't matter because they have the same solutions. And we do that in math all the time. Effectively, that's what algebra oftentimes is we're going to trade an equation for a simpler equation that happens to have the same solutions. We do that all the time in math. Okay, everybody get that? Yeah, they're still going to have the same zeros. Okay, all right. How about this one? This might even be overkill. Let's just set this one up at least, right? So what would I have to do here? Okay, I'm seeing people switch, pointing like we got to move some. I got to put in standard form, right? So I could divide each side through by 2x squared, or subtract 2x squared, sorry. Excuse me. So now I end up with 3x squared minus 21x plus 40 equals 0. So it's in standard form. Nothing else I can do. So now I would just have to throw that into the quadratic formula. So x equals negative b, that's 21, plus or minus the square root of negative 21 squared. We'll just square positive 21. Minus 4 times 3 times 40. Right, all divided by 2 times a. 2 times 3 is 6. Okay, so what's that going to give me then? I'm going to get 21 plus or minus the square root of 21 squared. What's that going to be? I'm going to get 20 times 21 is going to be 420 plus.
How do you get the 3?
Did I mess that up? Oh, you're right. It's supposed to be a. Oh, no, that's right. 4AC, right? So A is 3, C is 40. So I get B squared minus 4 times A times C.
Okay, so I think I was getting confused because I'm trying to make into just having A equal 1.
Oh, no, we don't want to do that in this case, because if I just make A equal 1, then I'm going to get fractions, right? Yeah. See what I'm saying? So we want to have integers there, okay? Sometimes, like in the last example, did we have that in the last example? We were able to, okay, in the last example, we could make A1 because I could divide 4 evenly into all parts, A, B, and C, okay? But in this case, we can't do that. So we just leave the values as A equals 3, B equals negative 21, C equals 40. We do not want to have fractions. Fractions makes this very messy, okay? All right, so this is going to give us, what, 441 minus, let's see, 3 times 40 would be 12, would be 120, times 4 is 480. Okay, all divided by 6. So what can we do here? This is going to give us up here, we're going to get a square root of negative 39. Looks like, is that right? 39? Yeah. Okay. So I'm going to get 21 over 6 plus or minus the square root of negative 39, which is going to be the square root of 39i, and there's no perfect square factors of 39, divided by 6. And so we end up getting, I can divide each of those by 2, right? So I get, or by 3. So I get 7/2 plus or minus the square root of 39 over 6i. Okay, I think I did all that right. Everybody with me on that? And they all just kind of look like that, right? They're all going to be similar problems. Some simplify more than others. Some end up the solutions look a little messier, but it's always the same process. Okay, what about this one? What would I do here? And I don't have to do anything. I could use that as it's written, but what's a little bit ugly about that? About that equation as it's currently written? The decimals, okay. So what could I do to eliminate the decimals there and make the numbers a little bit easier to work with? The coefficients. Okay, good. I could just multiply by a big enough power of 10 so that I eliminate the decimals and turn those into integers, right? So I could just multiply through by 10 in this case. And that's okay to do, right? Multiplying, I have an equation, and I can always multiply both sides of an equation by the same constant, right? As long as it's not a variable, there's no problem with this. So I distribute the 10 through. It's going to move the decimal one place to the right, so I end up with 6x squared minus 36x minus 6 equals 0. And now what could I do? Okay, so now I can just divide by 6, okay? Or I could have divided by 0.6 at the start, too. That's a good point. Either way, if you saw that, that would have been a little bit quicker. Either way, these are two pretty easy steps. So if I divide, oh, sorry, what am I doing? I was saying divide by 0.6, and I meant just divide by 6. I do that all the time. My mouth gets in the way of my brain. Right? And we end up with x squared minus 6x minus 1 equals 0. Okay, now I just apply the quadratic formula again. So I'm going to get x equals negative b, which is 6, plus or minus the square root of negative 6 squared, which is the same as positive 6 squared. So that's just going to be a 36, right? Minus 4 times 1 times negative 1. Now, I just want to show you a little trick here, divided by 2, right? Okay, so look over here. When I'm multiplying the 4 times a times c, I always know that if I have an even number of negative factors there, the result is going to be positive, isn't it? See what I'm saying? So look what happens here. If I'm subtracting 4 times 1 times negative 1, I'm actually subtracting a negative. And so one thing you can do here to just make the work a little bit easier, the math a little bit easier, is you could always say negative times negative is positive, right? And so then I end up with 6 plus or minus the square root of 36 plus 4, which is the square root of 40. Okay, now I can see that this radical is going to go away. 40 is not a perfect square. So let's go ahead and split these fractions up then. Okay, are you seeing this process? And so with you guys especially, a lot of what I like to do is I like to model a really efficient process for doing math. You can do this, you don't have to follow these exact steps, but if you just kind of try to model the way you do this around the process that I'm using, you'll see that it cuts down a few steps, right? Like I'm not going to write the denominators until I see if that's going to become an integer. If it becomes an integer, then I'll have one common denominator and it works fine. But if I'm going to be stuck with an irrational number here, I'm going to split these terms into separate terms. Okay, and so we end up then with 6 over 2 is 3, plus or minus. The square root of 40 we could reduce into what? That's going to be, I could take out a 4, so I get 2 radical 10, right? And the 2's will cancel, and so I get plus or minus the square root of 10. Those are my two results. How about that? Now, one really nice thing in Math Excel that I just figured out is when you're solving these when you're writing the solutions, it tells you to separate them with a comma. I'm pretty sure you can use the plus or minus symbol and it'll mark it correct. Okay, that's kind of nice that it does that. So you don't have to type it in twice. Okay, how we doing? Give me a 1 to 5, everybody. Okay, yeah, and this just takes a little practice, and that you're going to get a chance to practice all this. You'll feel totally on top of this here in a day or two. Okay, what would I have to do here? I won't even necessarily go through the whole problem, but what would I have to do here to solve this equation? Okay, FOIL me, I'd have to expand it out, wouldn't I? I have to put this into standard form. So I would have to multiply out these binomials, right? And if I do that, let's see, what am I going to get here? I'm going to distribute the 5x and get 10x squared plus 20x. I'm going to distribute the negative 1, and I'm going to get a minus 2x minus 4. And that whole thing is equal to 7x. Well, I could combine some like terms. So I get 10x squared plus 18x minus 4 equals 7x. And now all I've got to do is just push that 7x over to the left side. And I've got it. I've got this thing written as a quadratic function. In standard form. And now I just evaluate the quadratic formula and I got my solutions, right? But I got to put it into standard form first. Okay, so here's the next part, right? So let's think about this logically here. There's the structure of the quadratic formula gives us a strong hint about what the outcome is going to be when we solve the equation, okay? So if you look at the quadratic formula, isn't the part that's going to give us the i's potentially, right? The imaginary part is always going to be the result of having a negative number inside the square root, right? So we give that part of the quadratic formula that sits under the radical, we give that a special name. We call that the discriminant. And sometimes we will even assign that the capital D, stands for discriminant. And why is it the discriminant? Because it's going to discriminate for us between the real and the non-real results, right? Think about what we know here. We know that if the discriminant is positive, we're going to get two real solutions. There are not going to be any i's in there. Everybody agree? The only way we could get i's in our answer is if I have a negative discriminant. If it's positive, then I know I'm going to get two distinct real solutions, one for the plus symbol and one for the minus symbol, right? Okay, what if the discriminant is negative? Let's skip down to the bottom for a second. If the discriminant is negative, well, then I know I'm getting i's because I'm getting a negative number under the radical and I'm getting two solutions, one for the plus and one for the minus again. I get two imaginary solutions. And in fact, we even know a little bit more than that, right? We've already talked about this. I know that these two imaginary solutions are always going to look like complex conjugates. Right? If the discriminant is less than 0. Well, what if the discriminant is exactly equal to 0? If the discriminant is equal to 0, then we end up with a 0 under the square root, and the square root of 0 is just 0, right? So I get the result negative b plus or minus 0 divided by 2a. Well, those are the same solutions, right? Adding and subtracting 0 gives me the same result. And so if the discriminant is equal to 0, we get only one real solution, which we sometimes call a double root because it actually counts for 2. The two solutions just converge on the same answer twice, but I only get one unique solution there, okay? So far, so good? Let's back up to the top for just a second, because if the discriminant is positive, we can even do one more little thing that's kind of useful. If the discriminant is a perfect square, then we know that the square root part is going to disappear when we simplify, right? So I know I'm going to get two solutions that are rational. Okay, they can be written as fractions. If the discriminant is not a perfect square, I'm guaranteed that I'm going to get something stuck under the radical, right? The couples might go out, but the singles are going to stay in, and I'm going to get stuck with a square root in my answer. And so I know that I get two solutions that are irrational. They cannot be written as fractions or as decimals, as terminating or repeating decimals, right? Okay, so let's practice this discriminant stuff just a little bit. First of all, let's you guys just, these are your notes. If you want to fill these in on your notes, you're fine. I mean, you may or may not be writing the notes down as you go. I don't care. I publish the notes online every day. So at this level in an advanced class, I don't care if you're writing all this stuff down. All the information's there in my instructional notes, and everybody knows how to find that, right? That I just want to make sure. I mean, that's crucial that you can find you just go to classwork, you go to course information and resources, and you go to my instructional notes, and then this is updated every day. So if I go up to Unit 4, the unit we're on, there they all are, right? So this ought to look familiar. If I pull up the 3.3, so that was notes on, and if you hover over these, it'll give you the full title. So that's solving quadratics with the quadratic formula. If I click on that, well, that probably looks pretty, whoops, got to load up. That looks pretty familiar. That's what we did last time, right? So there's all my notes. Everything is there every time. You always can, there's your notes for you, okay? But just for your own kind of just, maybe for just memorization purposes to help you internalize all this, let's fill these things in, okay? So what is the formula for the discriminant? Let's see, I'll ask a few questions here. So Sarah, what's the formula for the discriminant?
Isn't it just like the negative, or the b squared minus 4ac?
There you go, 4 squared, or b squared minus 4ac. So if the discriminant is positive and it's a perfect square, how many roots are we going to get? How many solutions are we going to get if the discriminant is positive? Hold up fingers. 2. Okay, good. I get 2 solutions or roots. And what can you tell me about those if D is a perfect square? Type it in chat for me. Okay, good. They're rational, aren't they? Good. Okay, what if D is greater than 0? So D is positive. Well, we know we're getting 2 again. What if it's not a perfect square? What can you tell me about the types of roots? Irrational. Good. What if D is equal to 0? Hold up fingers. How many roots do we get? 1. Okay, good. We get 1, and it is going to be rational, isn't it? right? Because there's no longer a square root. And if d is less than 0, so d is negative, how many hold up fingers? 2, good. And what are they going to be? They're going to be complex with imaginary parts. Okay, good? All right, we'll call our quits for today. The bell rang. Have a great weekend. Enjoy the sunshine. I'm here after school if you need me. If not, I'll see you on Tuesday.